Biomass and plastics are both carbon-rich materials. When we burn them, we mainly turn that carbon into heat, CO2, and water vapor, plus some ash and pollutants. In this video, we look at another option, dry thermochemical processes, mainly pyrolysis and gasification to convert waste into fuels and chemicals. Dry thermochemical processes convert waste without using water as the main reaction medium. So, unlike hydrothermal technologies, the feedstock must be quite dry before it goes into the reactor. And the process runs at atmospheric pressure or only slightly above. Moisture is usually brought down to around 10 to 15 weight% or less for good process efficiency. The key control knob is oxygen supply. With no oxygen, we have technologies such as torrefaction and pyrolysis. With limited oxygen or steam below what is needed for full combustion, we have gasification. Now, let's talk about pyrolysis. Pyrolysis is a thermal decomposition of waste at high temperature in the absence of oxygen into three fractions: oil, gas, and char. Because no oxygen is present, less CO2 is formed and emissions can be lower than incineration. There are different types of pyrolysis at different speeds and intensities. Torrefaction, about 200 to 300 degrees Celsius for tens of minutes. Biomass dries, loses volatiles, becomes more brittle and energy dense, but stays solid. Slow pyrolysis, higher temperature with minutes to hours of residence times. It maximizes char with smaller amount of gas and liquid. Fast pyrolysis, with seconds of residence times and very high heating rates. It maximizes liquid oil with less char and gas. And finally, flash pyrolysis, with even faster heating at sub-second residence times, driving rapid conversion to vapors that are quickly condensed into an oil. For plastics, the picture is different. In plastic pyrolysis, long polymer chains like PE and PP are broken into smaller hydrocarbons at around 500 to 600 degrees Celsius without a catalyst. We mainly get heavy waxes. As temperature increases, waxes crack further into gases, light liquids, and a smaller fraction of aromatics, which can be used as precursors for fuels and chemicals. Mixed plastic waste is more complex due to contaminants. For example, PVC introduces chlorine, PET introduces oxygen and produces more gas and char, and that is why presorting and dehalogenation are important for plastic pyrolysis. So why pyrolysis is interesting? Liquids from biomass can be upgraded to drop-in fuels or used as fuel for a boiler. Liquids from plastics can be fed back to steam crackers as a substitute for fossil naphtha. The char fraction can be used as a soil amendment, a solid fuel, or as a precursor for activated carbon. The key challenges are tars, oil stability, and dealing with contaminants in real waste streams. Now let's talk about gasification. Gasification partially oxidizes biomass or plastics at higher temperature than pyrolysis. Typical gasification temperatures range from 750 to 1000 degrees Celsius, with air, oxygen, steam, or mixtures as a gasifying agent. The main product is a syngas, rich in carbon monoxide and hydrogen, with some carbon dioxide, methane, and tars. After gasification, we don't get clean syngas yet. The raw gas still contains dust, tars, acid gases, and alkali metals. So before it can be turned into fuels, chemicals, or power, it must go through gas cleaning. That is cooling, removing particles, condensing and cracking tars, and scrubbing out corrosive and toxic components. Syngas is already a useful fuel. We can burn it in boilers for heat or use it in gas engines and turbines for combined heat and power. But we can also upgrade it into liquid fuels or chemicals when we need higher energy density, easier transport, or specific products. One key route is Fischer-Tropsch synthesis, which converts syngas into liquid hydrocarbons. It runs in a reactor at about 200 to 300 degrees Celsius and around 20 bars over a solid catalyst. The reaction makes long-chain hydrocarbons, plus water and a lot of heat. So cooling and heat removal are major design challenges. The raw product then needs post-treatment like refining before it can become diesel or jet fuel. Fischer-Tropsch is already used at scale with coal and natural gas. With biomass-based syngas, the same process can produce low carbon or even net zero fuels. And Fischer-Tropsch is not the only option. Syngas can also be converted to methanol, which is a fuel and a platform chemical, or to synthetic methane, a gas that can replace natural gas for heating or power. For plastics, gasification can handle mixed or contaminated streams that are hard to recycle mechanically. The resultant syngas is more energy dense because plastics have higher heating values, often 40 to 45 megajoules per kilogram compared to 18 to 24 typical biomass. However, real waste gasification must deal with tars, soot, and acid gases, so gas cleaning is a major part of the plant design and cost. So how do they compare? Pyrolysis stops at the stage of liquids, gases, and char. It is attractive when we want liquid products or solid carbon, and we can upgrade them downstream. On the other hand, gasification pushes the conversion further to produce a clean syngas. It is attractive when we want a gaseous feedstocks for fuels, chemicals, or hydrogen. Both processes are sensitive to particle size and ash content. For example, fluidized bed gasifiers often require particles below 10 to 20 millimeters, while fast pyrolysis units prefer 1 to 2 millimeters particles to achieve very fast heating rates. Mineral ash, chlorine, and heavy metals can cause slagging, corrosion, and catalyst deactivation in these technologies. That's why good pretreatment and careful feedstock selection are essential, especially for waste plastics and mixed municipal solid waste. To summarize, dry thermochemical processes allow us to unlock the chemical value of biomass and plastics that are too contaminated, too mixed, or too degraded for mechanical recycling. In all cases, pyrolysis and gasification work much better when the feed is pretreated. It must be dried, ground to smaller size, and cleaned from stones, metals, and halogens. In the next video, we will look into wet thermochemical processes and see how they complement the dry processes you have just seen.